Hi, I'm Alex Marder, and I'm going to talk about Apple, which is a potential new direction for alias resolution. I'll start with a brief overview of the talk. First, I'll talk a little bit about what alias resolution is and why it's important, and two techniques that I view as the current state of the art. Then I'll dive into the Apple methodology that's comprised of two stages: building the potential router alias groups and then pruning them with pings from a bunch of different vantage points. Finally, I'll talk about results comparing Apple against two ground truth networks and wrap up with some ideas for future work. First, what is alias resolution? Briefly, it tries to figure out which router interface IP addresses are on the same physical router. Here, the left side of the slide is showing some traceroute segments with interface addresses, and the right side is showing which of those addresses belong to the same router. So why is that important? Well, Traceroute only provides router interface IP addresses, and those addresses by themselves don't give you any router identifiers. For a bunch of different types of analyses, a router level graph, which is the type produced by alias resolution, provides a more comprehensive view of the network. One important example is performing different resiliency assessments, where it can be important to identify interface addresses that share the same router level fate. So now I'll quickly go over what I think of as the current state of the art. The first set of tools, such as Ally, Radar Gun, and Marder, use the identification field in the IPv4 packet header. This IPID field was originally designed to enable packet fragmentation, and many routers populate the field using a shared global counter. What that means is that a router uses the same counter across all of its interfaces. So if you induce responses from two different interfaces on the same router, you might see that the IPID values for each interface increase at the same rate. And that's what I'm showing here in this handcrafted example. On the left, the IPID values for A and B increase at roughly the same rate or velocity, while on the right, they're clearly using different counters. And the second technique that I'll include as state-of-the-art is extracting router identifiers from DNS hostnames. Doing this on a large scale was only really made possible recently. And this new tool, called hoiho, uses IPID alias resolution as training data and automatically learns regular expressions that can extract router identifiers embedded in the hostnames. As an example, Phil and DAL3 at the bottom indicate different routers in Internet 2's network. So do we still need more than what we have? Well, obviously I think so. For the IPID techniques, they rely on specific implementations of the Internet Protocol with differences between manufacturers and OSs. Not all routers use a shared global counter to populate the IPID field, and some routers use random values, while others put 0 there unless they're fragmenting a packet. And in IPv6, the problem is even worse, because the standard IPv6 header doesn't include an IPID field. In order to use these techniques on IPv6, you first have to induce fragmentation. And then for DNS hostnames, we can't reverse look up many of the addresses that we see in Traceroute. And even the ones that we can look up often lack a useful router identifier. Basically, we don't have a single alias resolution technique to rule them all. Instead, we try to find some reliable techniques and then throw them all at the problem. So that brings me to my technique, Apple. The primary goal is to reduce reliance on specific implementations of IP and come up with something that can work for both IPv4 and IPv6. To do this, I first use Traceroute to produce candidate sets of router aliases. And then I prune those sets using pings from a bunch of different vantage points. So the reason I start with traceroutes is because traceroute responses generally indicate the inbound interface on a router. This is the router interface that received the traceroute probe. I call this common successor alias resolution. Basically, if two addresses, A and B, both precede the same interface in different traceroutes, there's a pretty good chance that they belong to the same router. So the first step is to build these sets of candidate aliases. I take the trace routes, turn them into an interface graph, and then build the sets of common successors. Obviously, there's well-known problems with this inbound assumption, which is why I don't use it by itself as alias resolution. For example, this isn't going to be true for multi-point-to-point links such as IXPs. Second, some routers don't always respond with the inbound interface address. Instead, they reply with an off-path address, usually the address of the interface that transmitted the traceroute reply. Third, when traceroute packets traverse an L3 VPN, the exit router responds with the outbound address. This is the address of the interface that would have continued forwarding the probe packet. And fourth, invisible MPLS tunnels can cause routers to falsely appear directly connected. And importantly, in all of these cases, A and B share a common successor, but do not belong to the same router. Alright, so this brings me to the second step, where I use information learned from the ping probing to prune the candidate groups of router aliases. When I send pings from a vantage point to an address, I'm trying to get an estimate of the reply path length. This is the router path that a reply takes to get from a router to a vantage point. Now obviously, I don't know the actual path that a reply takes, but I can get an estimate by looking at the TTL in the IP packet header. When a router originates a packet, it initializes the TTL field with some value, and subsequent routers decrement that value until the packet reaches the vantage point. So why use the reply TTL? Well, the routes from a vantage point to different addresses on a router might take very different paths. This is especially true when the different addresses have different longest matching prefixes in BGP. But quite often, the path from a router to a vantage point is the same regardless of the source address because of destination-based forwarding. And even if the router path is not exactly the same, for example with load balancing, the length of the path might still be the same. Basically, I'm going to use reply TTLs to discriminate between the potential router aliases in the common successor groups. If the reply TTLs match for two addresses, that suggests they might be on the same router, while different reply TTLs indicate that they might belong to different routers. Now there's always the chance of random reply TTL collisions, by which I mean that two addresses on different routers might have the same reply TTL to a vantage point. In fact, this is a virtual certainty. The TTL field is 8 bits, so there are only 256 possible values. And the values are likely not uniformly distributed, so some will be more likely than others. And for this reason, I don't just rely on the reply TTL to a single vantage point. Instead, I ping each address from every vantage point at my disposal. Before I discuss how I use the reply TTLs to keep or discard potential router aliases, I first need to talk about the natural trade-off between including more valid aliases and including some false aliases. And in general, I think it's better to limit false aliases potentially at the expense of reducing the coverage because of the transitive nature of alias resolution. And this is what I'm showing at the bottom of the slide. I have these two pre-existing router groupings, and I mistakenly keep the alias pair with addresses A and B. This then leads me to collapse the two router groups into one, and turn a single incorrect alias pair into 6 invalid alias pairs. So in Apple, I parameterized it with two different thresholds that control the trade-off I just mentioned. The first is the minimum match threshold, which determines how many vantage points need to have the same reply TTL for both addresses. And this helps limit the probability of a random collision. The second threshold, the acceptance threshold, dictates the minimum ratio of matching reply TTLs to comparisons. So to set the minimum match threshold, I use a generalized solution to the birthday problem to approximate the probability of a random collision. The birthday problem asks, given some number of people in a group, what is the probability that any two of them share a birthday? And I've put a common approximation of a generalized solution to this problem, on the slide, where n is the number of people in the group and d is the number of days in a year. Alright, at the risk of boring people to death with math, there's a couple of things worth noting about this equation. First, the n times n minus 1 over 2 term is the number of people pairs to compare. So this can be replaced by the total number of potential alias pairs, which are the pairs of addresses that Apple will test to see if they belong to the same router. The second thing is that d, which represents the number of days, really represents the total possible search space. So this can be replaced by the reply TTL search space, which is the number of possible reply TTLs raised to the number of vantage points included in the comparison. And the reason I raise it to the number of vantage points is that for each alias pair, I compare the reply TTL at each vantage point separately. Now for a traceroute collection, I already know the number of potential alias pairs, because that's dictated by the common successor groups from the traceroutes. And after I send the pings, I also know the number of possible reply TTL values. So when I set the minimum match threshold, which determines the minimum number of vantage points with matching reply TTLs, I set it such that the probability of a random collision is less than 1 in the number of possible alias pairs. Now I'm not suggesting that this is the definitive theoretical analysis, and I give some reasons why I think this underestimates the chances of collisions in the paper, but the main goal here is to try to eliminate as much risk of inferring a false alias pair as I can, while keeping enough real alias pairs to make it useful. So this is now I'm up to the second parameter, the acceptance threshold, which is a little easier to understand. It dictates how many comparisons are allowed before we reach the minimum match threshold. For an alias pair, I sort the vantage points by their minimum round-trip time to either of the addresses in the alias pair. And I do this because I normally expect that vantage points closer to the addresses are better discriminators than those further away. Basically, I think there's less of a chance that the reply will encounter a network technology that could mess up my approach. Then I compare the reply TTLs in sorted order until I reach the minimum number of required matches. So basically, the acceptance threshold tells us the minimum acceptable ratio of matches to comparisons. Alright, so now I'm going to use the potential alias pair B and E as an example. I pinged each from 8 different vantage points, and now I need to decide if I'm going to keep this alias pair or not. So the first thing I do is I sort my vantage points in order of reply of the round trip time. And if I require at least 6 matches, and I set the acceptance threshold to 100%, then I can't encounter a mismatch, so I start going down the list. And I keep going until I eventually get the required 6 matches. In this case, I didn't have any mismatches because I stopped before getting to the 7th comparison, so I include the pair. But if I had required 7 matches instead, that would have taken 8 comparisons. And since 7 out of 8 is less than 100%, we would have discarded the alias pair. And that's really the whole methodology that I use in Apple. Now, there are some pretty important limitations. The first is that this technique is potentially confounded by load-balanced paths of unequal length. Here, B and E are on the same router, but traversed paths with different numbers of routers. If this happened to a sufficient number of vantage points, then I'll incorrectly discard the pair. Even worse, there are times when I might incorrectly keep an alias pair. Here, A and B share the common successor F, but only because F was an off-path response. A and B are also on a load-balanced path between the router R3 and the router R4. So when I ping them, the replies always go through R3, creating the impression that A and B belong to the same router. And as I mentioned before, keeping invalid alias pairs is much worse than excluding a valid alias pair. Okay, so now that I've gone through the methodology, perhaps in too much detail, I can now talk about my experiments that evaluate Apple against ground truth from 2 networks. and I also compare Apple to existing IPID alias resolution techniques. I did a couple of experiments to get a sense for whether this approach could be useful. I used CAIDA's ITDKs, which include traceroutes and alias resolution. For IPv4, I used the April 2019 ITDK, which uses iffinder and Marder for alias resolution. That ITDK didn't include IPv6, so I used the January 2019 IPv6 ITDK, but sent the pings in May of that year. And the IPv6 ITDK used speedtrap for alias resolution. I also used CAIDA's ARC platform to send the pings, which gave me 99 vantage points for IPv4 and 78 vantage points for IPv6. And I got ground truth from two networks, Internet 2 and another RNE network in the United States. Now I know this isn't a lot of ground truth, and that both networks are RNE networks, and that's an important limitation of these experiments. In total, I validated against 67 routers with about 3,700 possible alias pairs in IPv4 and 57 routers with about 1,200 alias pairs in IPv6. After pinging all of the addresses in the common successor groups, I tried to get a sense for the reply TTL space in these experiments. What I did was for each vantage point, I selected the most frequent reply TTL and then computed the percentage of all replies at that vantage point accounted for by that most frequent reply TTL. Now I recognize that was a confusing sentence, so I'll try to explain it through an example. So let's say I have the two vantage points with the reply TTL seen on the left. And it's fine that they have different numbers of replies because an address might not respond to every vantage point. For the first vantage point, 56 is the most common reply TTL. Since it accounts for 2 of the 4 values seen at VP1, the most frequent reply TTL accounts for 50% of the replies at that vantage point. Similarly for VP2, 58 is the most frequent reply, and it accounts for 40% of the replies seen at VP2. So that analysis is what I'm showing in the graph on the left. For IPv4, there's no vantage point that has a single reply TTL account for more than 10% of its responses. This allows me to conservatively say that there are 10 possible reply TTL responses in IPv4 with uniform probability. And in IPv6, no vantage point has a single reply account for more than 20% of its responses, so I assumed 5 possible responses for IPv6. Then I took that estimate of the number of potential responses, along with the number of potential alias pairs, and increased the number of vantage points from 1 to 20. The idea was to find the minimum number of vantage points that gets the risk of random collisions below 1 in the number of potential alias pairs. In IPv4, that happened with 14 vantage points, and in IPv6, that happened with 17 vantage points. So in IPv4, in order to keep an alias pair, at least 14 of the vantage points must receive matching reply TTLs for both addresses in the pair. While in IPv6, I need at least 17 of them to match. The next thing I did was set the acceptance threshold. For this experiment, I fixed the minimum match threshold to the values determined on the last slide, and then increased the acceptance threshold from 0.15 to 1 to examine the trade-off between precision and the true positive rate. The left graph shows how the precision increases as the acceptance threshold increases, while the right graph shows that increasing the required ratio of matches to comparisons decreases the true positive rate. Most importantly, the left graph shows that an acceptance threshold of 0.78 eliminates all false positives in the ground truth for both IPv4 and IPv6. So for the remaining experiments, I set the acceptance threshold to 0.78 and just evaluate the true positive rate. So now I can finally show some results for the two ground truth networks. The left graphs for IPv4 and IPv6 show the true positive rates for Apple, the ITDK alias resolution, and the combination of the two. The right graphs show the number of pairs inferred by each alias resolution technique and the value of combining them. There are a few key takeaways, and they all come with the caveat that this is not a lot of ground truth. 1. The coverage for IPv4 is similar for Apple and for the ITDK. 2. Apple's coverage is a little bit better for IPv6 than IPv4. Third, and probably most important, Apple seems to combine well with Marder and IfFinder. Combining Apple with the ITDK alias resolution more than doubled the total number of alias pairs for the Traceroute collection. And this is important since I was trying to add a new tool to the alias resolution toolbox. And then the last experiment gives me some reason for concern. For this experiment, I artificially limited the number of vantage points in IPv4, creating groups of randomly selected vantage points ranging from 15 to 95 vantage points. For small numbers of vantage points, Apple had high precision but low coverage. In fact, some of the groups couldn't find a single alias pair for Internet 2. For larger numbers of vantage points, I started to get false alias pairs for Internet 2, but the coverage almost maxed out. And finally, once the number of vantage points reached 90, I didn't get any more false positives. Now, I said these results are a little concerning because it suggests that I might have gotten lucky with the set of vantage points for my main experiments. And truthfully, as I point out in more detail in the paper, I found anecdotal evidence of false alias pairs outside of the ground truth. So to wrap up, the main takeaways are 1, that Apple's coverage was roughly equivalent to Marder plus IfFinder for the April 2019 Traceroute collection. 2, it performed slightly better for IPv6 than for IPv4, showing that it can be an effective tool for IPv6 where alias resolution is desperately needed. And 3, it complements the alias resolution that's already used in the ITDK, so it can be another useful tool in the alias resolution toolkit. And then as future work, I hope to evaluate Apple against a much broader validation dataset. I'm thinking about using hoiho regular expressions to generate a pseudo ground truth, and hopefully by comparing against more ground truth, I can continue to improve the pruning step and further decrease false alias pairs. So that's what I have, and I'm happy to take any questions.